All right, today we will talk about the universal property of induced representations. So, so first let's recall the definition of induced representation. Uh, well, before that, let me tell you what does this universal property do? What is the importance of that? We have already seen the universal property of tensor products. So likewise, here also the universal property of induced representations characterizes induced representations uniquely. Okay, so now let's recall. So let G be a finite group, and let H be a subgroup of G, and H be a subgroup of G. Also assume that there is this is a, and rho is a representative finite dimensional complex representation of G. We restrict rho to H, which gives me a representation of H on the same vector space V. Let W be a subspace of V, which is H invariant, so that we can talk about the sub-representation of rho H on W. Let's denote that by theta. We now say theta induces rho if V happens to be the direct sum of W sigmas for every sigma belonging to G modulo H, where W sigma is defined as rho G of W. G is any representative, G is any G element of sigma, and we have already seen that whatever G we choose from sigma, this is always going to be the same. So therefore this definition does not have an ambiguity, doesn't. So thus we have defined when we say rho is induced by theta, then for an arbitrary representation, we say that lambda, so let me write, so we say that lambda induces lambda induces rho if lambda is lambda is isomorphic to a theta as above, which in so theta, if lambda is isomorphic to a theta, which is a sub-representation of the restriction, which and furthermore this theta induces rho. So let me again repeat. I say an arbitrary representation lambda induces rho if lambda is isomorphic to a sub-representation of the restriction which induces rho. So lambda is isomorphic to a theta like this, which induces rho. Okay. So now we will go for the universal property. So the universal property always involves with maps. So therefore the following is going to be a first step towards the universal property, which says that every H invariant linear map defined over W can be extended to a G invariant linear map over the whole of V. So let me write down the statement first. So assume that rho is induced by theta. Rho is induced by theta, and F is a map, and of course, and V prime rho prime is a representation of G, finite dimensional complex representation, and F from V W to V prime be H invariant. What I mean by this is, as expected, for every H in H, F compose theta H is rho prime H compose F. So again let me again let me tell you what let me repeat. So we assume that rho is induced by theta, where theta is a sub-representation of the restriction, and v prime rho prime is a representation of G, and assume that there is a H invariant linear map from a H invariant linear map from W to V. By H invariance I means this, that theta H, so there I mean precisely this. So now the lemma says there exist, so the lemma says that this F has a unique extension to a G invariant linear map to V. So there exists F from V to V prime, which is G invariant linear, and further so there is a, and which extends F, that is F of W is small f of W for every W in W. Okay. So F was an H invariant linear map which extends now to a G invariant linear map to the whole of V. Okay, so this shows that such an extension is also unique. So let's now go for its proof. The proof of this is again not difficult. Recall, since rho is induced by theta. So well, first let's do the proof in this way, that first we will show the uniqueness, then we will show the existence. So that is, first we will show that if at all there is an F such that this happens, then that F must be unique. Okay. So that we will see in this in the following way. Recall that since rho is induced by theta, so recall that this is what we have. This is what we have. So for our convenience, what we do is from each of these cosets we will choose a representative GI. So what and write the sum in terms of GIs. So again, what have done is, suppose sigma 1 up to sigma k are the cosets of H in G modulo H. So from sigma I will choose a representative GI, so that now W sigma becomes rho GI of W. So therefore we write this sum as this. What does that show? That shows that if you take any typical term GI, if you take any typical term here, so any x belonging here, you see that rho GI inverse x belongs to W, right? Okay, so when since this belongs to W, that means that we can write f of x as f of rho GI, compose rho GI inverse x. Okay, fine. So what is this? Since we know, so since f is assumed to be G invariant, then that means this has to be rho prime GI of if compose rho prime GI of rho GI inverse x. Okay, now you see that rho prime GI. So what is, so since this belongs to W, and by assumption if capital F in extends small f, so this is nothing but this fellow just becomes f of rho GI inverse x. Okay. So therefore you see that for every f, so if f is a G invariant linear map on if f is a G invariant linear map on V that extends small f, then on every summand if you take any summand, then for every x belonging to that summand, f of x must be this. And this just involves the function f small f which is given to us and the representations. So again, let me repeat. You see that if at all there is an f with the required properties, then for every x belonging to a typical summand, the value of the function at the point x must be this. So that shows that f is unique on each of these summands, and since since v is the direct summand of all these, so from that it proves that if there at all there is an f, that must be unique. So this proves the uniqueness. Now we shall prove the existence. Existence. The reason for proving uniqueness first, the reason for proving the uniqueness first is that that in fact shows us the path how to show the existence, how to establish the existence, and we will precisely do that. So now our job is to define an x. Okay, so our job is to define an x, sorry, define a function f. Okay, so how to define that? So since it is given that f is since we are supposed to define a linear map on this direct summand, so it's enough to define f on each of them, because once we have defined a G invariant linear map from each of these subspaces, therefore from the universal property of the direct sum, we will get a map from the whole V to V prime, a G invariant linear map in fact. So we wish to define f on every G sigma. Okay, so we define enough to define f on each W sigma. Okay, good. So how to define that? So let we write W sigma as rho G of W, where G belongs to sigma. So the proof of uniqueness suggests us to define for each x in W sigma, f of x as the rho G inverse, rho prime G inverse, f of well, here actually I don't need bracket, rho G, okay, inverse, sorry, I should not put inverse everywhere. So here rather here I have an inverse, rho G inverse x. Okay, we have to just prove that this does not depend on the choice of G, and that is very easy to see, because if instead of G we take some other representative, which will take, if we take some other representative, then that will be some GH where H belongs to H. Now you see that this rho prime GH is rho prime G, rho prime H, F rho H inverse, F rho H inverse, rho G inverse X, right? Fine. Then what we do is we have to show that this is exactly equals to this. Okay. So now recall that F is H invariant. So therefore rho prime G of rho h, rho h inverse, rho g inverse of x. Now it is there because this guy, so the composition of these two becomes identity, so therefore this exactly, so this part goes away, hence we see they are the same. So thus on each sigma, which is, I remember that each sigma is a subspace, each sigma is a vector space in fact. So on each sigma I have this f, okay, I have this f, and by its construction, so on each sigma I have this f, and yeah, and the definition that it shows that f is all linear as well, because small f is linear. So thus on each of this summand I have a linear map. Therefore from the universal property of direct sum, we get a map from v to v prime, which is a linear map. And the g invariance of this linear map is also quite easy. I just leave the routine verification to you. Recall that this the g invariance of this map follows from its very construction on each of these pieces. Okay, fine. So that so therefore I leave this easy verification to you. Yeah, therefore we have proved this lemma. Okay, so using this lemma, let's using this lemma we shall first prove that yeah, using this lemma we shall prove that if, well, how to put it, okay, so this lemma plays an instrumental role in proving the uniqueness of induced representations. That is, if for a given lambda there are two representations which are induced by lambda, then these two representations are isomorphic. That's what we will prove, and this lemma is going to play an instrumental role there. So let's do that. That's better. So therefore uniqueness of induced representations, let's try to prove that. Okay, so assume that h has yeah, so yeah, so maybe we put that in this way. Suppose rho is induced by theta, okay, and also another representation, let's say rho prime is also induced by theta. So let this be the space be v rho, and here the space be v prime, the vector space be v prime. We will show that there is a g invariant linear isomorphism from v to v prime. Okay, how to prove this, how to prove that? That's very easy. So so recall that in general terms a representation v, recall that in general terms a representation rho is induced by a representation. That means that there is a sub representation of the restriction that induces that. So whenever we have a representation which is induced by another representation lambda, so what, well, let me go back to the previous page. So if whenever I have a arbitrary representation lambda which induces this rho, then what we can do is we can identify this lambda with the sub representation of the restriction theta. So without any loss in generality we can do that because of the isomorphism. So here what we do is we assume that So without any loss in generality, we will assume that theta is a sub-representation of rho h. So in view of this identification, therefore it does not matter if your yeah. So in view of this identification, it doesn't matter if you just think the representation which inducing is a sub-representation of the restriction. So we shall assume that, and also yeah, and also rho prime is induced by theta. Rho prime is induced by theta. So what does that mean? It means that this v prime has a sub h invariant subspace w prime. V prime has a H invariant subspace W prime such that the restriction of rho prime H on W prime is the sub representation of rho prime H on W prime induces rho prime, and that then sub representation is isomorphic to theta. So what I mean by this is, so what we have is, so what we have here is, so there exists an isomorphism phi from W to W prime. So where W is the space of theta. So there is a, so since from the definition there is a H isomorphism. Uh, so here isomorphism of representations of H, because both W and W prime are representations of H. So phi is a H invariant linear isomorphism. Okay. So this comes from the definition of a representation. Now recall that W prime is contained inside V prime. So therefore theta is a H invariant linear map from W to V prime from the previous lemma that extends to a phi from V to V prime, which is a G invariant linear map, and this extension is also a linear map. This extension is also so yeah, this extension is G invariant. Okay, fine. Now it is very easy to see that this is in fact so this is a G invariant linear map. All that we have to prove is this is a bijection. So this is very easy to see. First of all, we will first see that both V and V prime have the same dimension. So they have the same dimension. Then it will be enough to prove either injective or surjective, whichever is convenient, in order to show this is bijective. Now, since both rho and rho prime are induced by theta, so therefore the dimension of V becomes this times dimension of W from the dimension formula, and dimension of V prime also becomes the same, but dimension of W prime. But since W and W prime are isomorphic, so the dimension of dimension. So therefore, these two are same. So hence this map is so yeah, both V and V prime has the same dimension. Now we will just show that this map is indeed surjective. So subjectivity is again in view of the fact that V decomposes as W sigmas. Let's for convenience, let's write that in this form. W, so where G1 up to Gk is a complete set of representatives of the cosets. Now you see that since phi extends, so this capital phi extends small phi, so therefore therefore the image of a typical summand, what the image is nothing but, if we see from the invariance of phi, it follows that phi prime g1 times w prime. Okay, and now you remember, since v prime is the direct sum of these fellows, v prime is the direct sum of these fellows, therefore this maps becomes onto, because you see that each each some direct summand of this, each direct summand of this space is contained in the image of phi, so that shows this map is onto. So now this map becomes a linear isomorphism which is G invariant. So again, let me repeat the proof. So suppose I have two representations which are induced by a given representation theta. Suppose I have two representations which are given by a representation of theta. So without any loss in generality, we can assume that this theta is is basically the sub-representation of the restriction of one of them. Without any loss of generality, we can assume from the definition. So therefore, now simply I will assume that W is inside V, because of, so I can do that. And once we have done that, just for simplicity, we will do it next. So yeah, though that is, so that makes it basically simple to manipulate. Well, so once we have assumed that theta is in a sense contained in the sense, means it's isomorphic. So after the assumption that W is H invariance of space of V, then we have an isomorphism from W to W prime. So this isomorphism is there because theta also induces rho prime. So there, that means rho prime H has a sub-representation, let's say on W prime, which is isomorphic to theta. So let phi be the isomorphism. Now we extend that isomorphism and show that that gives an isomorphism of G invariant linear maps. So this shows the uniqueness of, so this shows that given any theta, if it has to, if there are two representations of G which are induced by theta, then these two representations must be isomorphic. Now we will show that so this shows, so what I have just said, that shows that if two representations are induced by theta, then they must be isomorphic. That does not guarantee whether any representation is there, whether there is any representation which is induced by theta. Now we will show that. So to show that that induces, so to show that for any theta there is a representation of for any theta there is a representation which is induced by theta. I'm saying that it's enough to show when theta is irreducible, because theta can be written as a sum of irreducible representations. And suppose I can prove the existence for any irreducible representation, then from that, in view of the result that if rho 1 is induced by theta 1 and rho 2 is induced by theta 2, so rho 1 direct sum rho 2 is induced by theta 1 direct sum theta 2. So in view of that, if we have that for each irreducible representation there is a representation induced by that, then in view of this we get that for any representation theta there is a representation induced by this theta. Okay, so now we can assume theta is irreducible. Okay, so every irreducible representation of H is contained in LH, right? So the left regular representation of H. So theta is isomorphic to a sub-representation of LH. Okay. Now what is LH? LH has the space. LH is the span of EH, right? So LH is So LH is the span of EH, right? Okay. So we now observe that LH can be viewed as a subspace of LG. Please be careful. Here the containment is the following, that every function defined over H can be viewed as a function defined over G if you put the value 0 at every point outside H. Okay. So I mean, a priori at the first look you may not agree, but here the functions are defined on H, but where, so how can I say that every function defined over H is a function defined over G? That is what we do is we put 0 elsewhere. Okay. So so therefore, in after this identification, you see that this we will view each EH as the elements in EG. So so now we recall that from the first example in last video, that this LH, so this subrepresentation of the left regular representation on this LH induces the left regular representation of G, right? Again, let me repeat what I am doing. This representation is in the so theta is contained as a irreducible subrepresentation of LH. Okay, so therefore let's say W prime be the subspace of LH, which is invariant under H, right? And where this subrepresentation is happening, which is isomorphic to theta. Let's write W1 instead. So now we view LH as a subspace of LG after proper identification. Now, and recall that once we have done that, once we have identified each LH, once we have identified each identified LH as a subspace of LG, then from that it becomes clear that the left regular representation of H is nothing but the restriction of the left regular representation of G on H. Okay, because both of them has the same thing, H applied on, let's say, E X is basically E H X. This is what we have for both H and X in H. So the left regular representation is the restriction of on H is the restriction of the left regular representation on G. So once we see that, then we recall that this restriction this restriction induces the left regular representation of G. And since W1 is a H invariant subspace of that, then all the translations of W1, all the translations of W1, GI, all the translations of W1, this becomes a G invariant subspace of LG, right? And hence the subrepresentation of the left regular representation of G, the subrepresentation of R, which R is the left regular representation of G on this subspace, is induced by the subrepresentation of the left regular representation of LH on W1. So try to understand the proof. First, we have we have used that theta is contained as a subrepresentation of LH, and let W1 be the space of the subrepresentation. Now we see LH as a subspace of LG, and as well the left regular representation of H as a restriction of the left regular representation of G on H. Once we have done that, then since this left regular representation, since this the restriction of the left regular representation on H induces the left regular representation of G. So therefore, being an invariant H is subspace of W1, this space becomes G invariant. So therefore the subrepresentation of the left regular representation of G on this subspace becomes induced by the subrepresentation on W1. So that is exactly we need to show, because the subrepresentation of W1 is isomorphic to theta, and this subrepresentation induces this representation. So therefore theta induces this representation. Theta induces this this representation, that is the subrepresentation of R on this space. Okay, so thus we have settled both existence and uniqueness part. I will just finish with one yeah. So I will just finish with one more remark, which I would rather leave to you as an exercise. So the remark is, so home H between W and V prime is isomorphic to home G between V and V prime, where V rho is induced by W theta, and V prime rho prime is a representation of G. Okay. So earlier what we have proved is every element here through an extension can be viewed as an element here. So every small f here gives rise to every small f here gives rise. So home H means set of all H invariant linear map this between W and V prime, and home G means set of all G invariant linear maps. So earlier what we have seen, each f gives rise to a capital F here. Now what I am saying is that assignment sending small f to capital F, in fact that establishes a linear isomorphism between these two spaces. That's what we will sorry, that's what I am leaving to you as an exercise. Okay, so yeah, and before we finish, I will just again summarize the universal property of this induced representations. So what it says, that given a representation W theta of H, given a representation W theta of H, so this universal property given theta of H, there exists unique, again unique means unique up to isomorphism, v rho of G with the following two properties. What are the properties? Property 1 says, first of all there exists W there exists a W, let's say W bar subspace of V, which is H invariant, and an isomorphism from W to W bar H invariant. So this means that rho has a, this says that the first property says that theta is isomorphic to a subrepresentation of rho H. So yeah, theta is isomorphic to a subrepresentation of rho H. So this H invariant W bar is gives a subrepresentation of rho H on W bar, and this is isomorphic to theta. And property 2 is what it says, that is the, like every universal property, the extension of the linear map. So what say the second property says that suppose V prime rho prime is a representation of G, and F is a map from W to V prime, linear map H invariant linear, then there exists unique F from V to v prime, in the sense that this f extends small f, that is so such that such that f of since f is from defined from v, and so therefore how we should write is f phi of w is simply f of w for every w in w. So this is what I have to write, because W may not be contained inside a row in the beginning. So while when we say that it extends, that is it extends. So yeah, so since W is identified with W bar, so this F we can regard as a map, H invariant map from W bar, and technically this F extends that that H invariant map from W bar to a G invariant map to H. So therefore, this is what the correct formulation. So this is what the universal property of induced representations, and we have proved this. We have proved this. So this existence part is precisely the existence part of induced representation. We have, as I so the induced representation, that is, we have first shown that the induced representation exists, and induced representation satisfies these two properties. Yeah, so the property one is just follows from the definition of the induced representation induced by W theta, and property two is just this. Property 2 is just this. So just we made for our convenience, without any loss in generality, we just assume that the W theta we begin with is actually indeed the W is a H invariant subspace of one of them. That we have assumed without any loss in generality to to for our convenience, so that when we write things, the expressions become less complicated. But this is actually yeah, without any loss in generality, and this doesn't make any difference. So we have proved that the induced representation of the representation induced by W theta satisfies these two properties. Now now we have to prove that in order to settle the universal property, that if V theta satisfies these two properties, then V theta must be the induced representation. And that will also follow from these two properties, property 2, the way we prove uniqueness of the object from any universal property. That's a routine one, hence I'm leaving that to you. So with that I will stop.